SwayamPrabha. Digital India. Educated India.
So, we are going to continue from where we left off, okay, and rather than rederive everything towards the end, I think I was going a bit fast. So, I just thought I will do a little bit of a recap. So, this is the gradient of V which we found out in the last class, okay, and this is the velocity vector. I wanted to point out that you get these extra terms because of the fact that when you take the derivative of the unit vector in the theta direction, it is non-zero, and that gives you these extra terms. Actually, this term arises here, and then because the e theta we moved it here, and again this term arises here and we moved it here because of the component. So, I was just trying to tell you which component it is. This is ER, this is E theta ER, this is EZ ER. So, when it comes to doing V dotted gradient of V, what I told you in the last class was, because you are doing the dot product, you take the dot of the unit vectors adjacent, which is one way to do it. Another way to do it is just to do something like a matrix multiplication, because we can just say this is a 1 by 3, 1 row 3 columns, and this 3 by 3, when you multiply it you will get a 1 by 3, okay. So, if you do just a matrix multiplication, you take, I mean, if you want to do the dot product, then you have to look at this ER dotted with ER, this E theta dotted with E theta, this EZ dotted with this EZ. That will give you 1. What is remaining is ER, which tells you that it is contributing to the radial direction momentum balance. You understand? That is what we did last time. If you look at this row and do the multiplication with this, it's the same as doing the dot product. This ER dotted with this ER will give you E theta. This E theta dotted with this E theta will give me this E theta remains. This EZ dotted with this EZ, this E theta remains. So, this will give me my theta direction momentum balance, the inertial terms. Similarly, this multiplied by this will give me the Z direction. So, this V dot del V can also be found by matrix multiplication, okay. So, I will just explain. So, for example, the first row of V, no, the only one row of V and first column of V, of gradient of V, give the inertial terms in the R direction. So, did this multiplication, what will I get? VR dVR by dr plus d theta dVr by d theta minus v theta by r plus Vz d by dz of Vr. So, actually I wrote it correctly. I thought I made a mistake somewhere. So, I think it is correct. So, this is what I would get, okay. This is same as doing the dot product of this with this and keeping in mind Vr dotted with this ER, this ER and this ER gives me 1, ER remains. This E theta and this first E theta gives me 1, ER remains. this Ez and this Ez gives me 1 Er remains, because Er I get the radial direction. Okay. So, I just wanted to show you that you can do it either using matrix multiplication or this method, whichever is comfortable for you. Okay. So, this is gradient of V. Now, what is gradient of V transpose? So, now I am going to write gradient of V without putting all these R and all that. Okay. dVr by dr, dV theta by dr, dVz by dr, and I get 1 by r dVr by d theta minus V theta by r, then I have Vr by r plus 1 by r dV theta by dr, dV theta by d theta, sorry, dV theta by d theta plus, not plus, dVz by r d theta. Then this guy is harmless, I get the same thing. Okay, dV r by dz, then I have dV theta by dz and dVz by dz. I need to find, if I want to find the shear stress, what do I have to do? I have to add the gradient of V transpose to this, okay, and then multiply it by mu, because I want to get a symmetric matrix, because tau has this property of symmetry. Okay. So, you can calculate what is gradient of V transpose, which it will be dVr by dr. Now, this gets interchanged by d theta minus V theta by r. All I am doing is doing the transpose, dVr by dz and so on and so forth, dV theta by dr. Okay. This comes here, the diagonal remains as it is, d theta, then I have dVz, oh what a minute, dV theta by dz and I am running out of space. So, this will be dVz by dr and this will be dVz by r d theta and this will be Vzz. Okay. So, I found the transpose of gradient of V by doing what is normally done. I am going to add del V and del V transpose. When I do that, I will get a symmetric matrix. Okay. And you can see that you will get a symmetric matrix. So, tau is going to be mu times del V plus del V transpose, and that gives me mu times dVr by 2 times dVr by dr okay. Then I have this will be dV theta by dr plus 1 by r dVr by d theta minus V theta by r plus dVz by dr dVr by dz. So, those are the first three. I only have to write the terms along the diagonal and above it, because below it, because of symmetry, it will be the same. Okay, so I am not going to do that. I will just write the diagonal elements now. The diagonal element will be 2 times VR by R plus 1 by R dV theta by d theta, okay, and this will be 2 times dV z by dz, and this term here will be dVz by dr plus dVr by dz, okay. I am saying that this term and this term are the same, this term and this term are the same, and this term and this term are the same, because it is symmetric now, okay. So, this is how you would go. So, basically what I am trying to tell you is that there is a systematic method by which all these mathematics is done. I mean, it is not that so you have to understand the process behind the mathematics, then I think you will be able to appreciate things better, right? And you do not have to, so at least you should know how to go about deriving it. You should be able to find out how to go about getting these calculations. So, this particular term here is tau r theta, which is the same as tau theta r, okay. So, tau r theta is going to be given by this dV theta by dr minus v theta by r plus dVr by r d theta. We are going to use this in one of the problems later on, and that is the reason I am making this point. So, tau r theta can be written as I want to combine these two terms, okay, the first two terms, d by d theta of r v theta, is it, or v theta by r? Theta. Okay. So, if I do the product rule of differentiation, what will I get? dV theta by dr minus v theta by r square r, I will get the same thing. So, all I have done is group these two terms together into one term, because when you look at some books, they will have different ways of expressing these terms, and you have to understand that they are just equivalent ways of expressing, okay. So, you should now be in a position where you can actually sit down and do some if you look at some equations, you should be in a position to at least be confident of trying to derive those equations. That is the whole idea. Why am I going through all this? Tomorrow when you see something, you should be able to get the same equations by following a systematic process, if you have understood whatever we are doing, okay. So, now this is as far as finding the shear stress is concerned, okay. What I want to do is, I want to do a kind of a simpler exercise, but just to go through with the whole thing. Supposing we want to do del square f, where f is a scalar. It is not a vector, basically it could be a function of x, y, z, that is what I mean. For example, this kind of system, this kind of problem will arise when you are looking at mass transfer and heat transfer, where F will be temperature. In the case of heat transfer, it comes from the diffusion, the Fourier's law of heat conduction. In case of mass transfer, fixed law of diffusion will give me del square C, okay. So, F is temperature or C for heat and mass transfer, Okay. So, how does one go about evaluating del square in the in let us say cylindrical coordinates? Okay. So, del square is nothing but, I mean, if you remember your vectorial calculus, del dot del of C is what we have to calculate now. Okay. So, I am going to talk about finding del dot del, and the nice thing is your assignment of course is del dot del of V, okay, but we are not going to do del dot del of V, we are going to do del dot del of C, which is a scalar. So, in the cylindrical coordinates, I write del dot del as what? ER d by dr, okay, plus E theta by r d by d theta plus Ez d by dz dotted with ER d by dr plus E theta by r d theta and d by d theta of that plus Ez d by dz. Okay, this is just a del operator. I have just written the del operator 2 times and this is a dot product. Del square, the Laplacian is defined as del dot del. Yeah. Which one? This one? You are talking about here? This one? Dou by dou r, is it? Yeah, yeah, thank you. Okay. You are right, otherwise I won't get the minus 1 by r square. Thank you. Yeah. Yeah. So, this is yeah, d by dr. Good. I was afraid that everybody is confused. I guess people are not confused. So, I can go a bit fast now. Okay. Yeah, that's good. Don't worry, I won't go too fast. Yeah, you are right, man. Thank you. So, this is kind of easy to do in the sense they have already done it. So, I am not going to go through the whole process again. Okay. When you are differentiating with respect to r, there is no change in the unit vectors, right. We already saw that. When you change r, the E theta and ER and EZ are constant. So, I can treat these as constant. I do not have to apply product rule. Okay. And so, the only thing which is going to contribute is ER dotted ER. This will be the only term contributing because ER dotted E theta is 0, ER dotted with EZ is 0. Okay. So, this is going to give me dVr by, oh sorry, no V, d by dr of d by dr, which is d square by dr squared. I am not telling you what I am operating on, okay, it is not a vector, it is either concentration or temperature, okay, which is a function of r theta z. So, basically I am trying to tell you how to evaluate the Laplacian for cylindrical coordinates, okay, which arises when you use Fourier's law of heat conduction and Fick's law of diffusion. So, only this term will contribute, agreed? Now, when it comes to this term, I have to be a bit careful because now the derivative is with respect to theta, okay, and therefore, when I differentiate ER with respect to theta, what do I get? I get E theta, okay, we saw that last time. So, now I will apply the product rule, I will get E theta by R d by d theta of ER plus d square by what am I doing? E theta is here, derivative with respect to theta, okay, plus ER is here, and I got confused now. I have taken care of this. I am looking at this guy, okay, d square by dr d theta r er. This is this term and this is this term. Is that right? No, no, that is not this term. Sorry. This is this term. I have applied the derivative with respect to theta of ER and derivative with respect to theta of the second term, product rule. Okay, I am basically doing a product rule here, but I am keeping in mind that ER changes with theta. So this guy will not contribute because the dot here, E theta dotted with ER will be 0, but this is E theta. Okay, so this is E theta, and therefore E theta dotted with E theta will be something. So how r d theta. So I have 1 by r. Okay. Similarly, you do the product rule of this guy, this term and the second term. So I am saying this is E theta by r. Oh, maybe I should do this a bit more carefully. I should have planned this better. I thought I would be able to do it. Okay. So when I differentiate this thing, when I take the derivative of this here, what do I get? Plus E theta by r d theta dotted with the second term, which is let me take the d by d theta here, okay, d by d theta of E theta differentiating E theta times d by r d theta plus E theta times d square by d theta squared times r squared times r. What have I done here? I am taking this term, I am doing the dot with the second term here. Okay, this is also a vector. So I am taking this term, doing the dot with this, applying product rule. Again, what you see is this will not contribute because d theta by d theta is minus ER. ER is perpendicular to E theta. So this does not contribute, only this contributes, and this gives me d square by r square d theta squared. That is this term. Okay, and the last thing is of course very nice because d by dz, with z nothing is going to change. So Ez dotted ER is 0, Ez dotted E theta is 0, Ez dot Ez is 1. So I get d square by dz squared. So basically what I am trying to tell you is del square of C will be d square by dr squared plus 1 by r plus 1 by r square d square by d theta squared plus d square by dz squared of C. Okay, and what people do is they like to combine these two guys as 1 by r d by dr of r d by dr plus 1 by r squared d square by d theta squared plus d square by dz squared of C. So we combine these two, do the product rule, what do I get? I get d square C by dr squared plus 1 by r d by dr I am getting. I missed a d by dr here. Why did I miss the d by dr? Yeah, this d by dr is missing. See, I am differentiating this with respect to I'm doing the derivative of this, right. So first function is ER, derivative of ER with respect to theta is E theta, plus I have E theta dotted with ER I missed this d by dr when I was doing the dot product. Okay, you understand what I did? I just got excited, I just differentiated this with respect to E theta and I forgot this d by dr. Okay, that gives me the d by dr and that now it's fine. Okay, so this d by dr I missed, I just have to add that, which I have done here. Okay, so I mean basically you need to learn to, there is no point in me doing all the identity, you have to spend some time, do things, you'll make mistakes, get it right and learn. Okay, so that's one way, in fact that's the only way. So okay, all these equations are fine, I mean at the end of the day we have to do something useful. So supposing you want to calculate the viscosity of a liquid, the way you go about calculating the viscosity of a liquid experimentally is by using a viscometer. Okay, and the way the viscometer works is there will be one surface which is solid and stationary, and there will be another surface which will actually be moving, and the liquid whose viscosity you are interested in finding is going to be between these two surfaces. Okay, and what you do is you shear the liquid, you move one of the plates, one of the walls, and you induce a velocity field. When you induce a velocity field, there will be some stresses developed, there will be some forces, some torque developed. You calculate the force or the torque and then you estimate what the viscosity is. This is the general idea. Okay, so you have different designs of viscometers. Okay, and you have a cone and plate, parallel plate, all kinds of designs are there. So we'll start with basically what I'm saying is to measure viscosity of a liquid, there will usually be a solid, stationary boundary, there is the liquid here and there is a wall here. This is a which moves, okay, at a particular velocity, moves at a particular velocity. Then this is basically called a shear driven flow as opposed to a pressure driven flow where there is a pressure gradient which is driving the flow. So the top plate is moving, okay, because of that it will drag the fluid next to it, adjacent to it, that guy will drag the fluid adjacent to it, that guy will drag the fluid adjacent to it, and you have a flow field established. Okay. So now we find something like either force or torque on the upper or moving wall, okay, and find the viscosity. I will explain to you what exactly we mean. I mean this is something called a Couette flow which most of you are familiar with, okay. So and then we will take it to the next level where we do the problem in cylindrical coordinates, okay. So we will now look at Couette flow. So we will do Couette flow in Cartesian coordinates and then we will do something in cylindrical. So, this is the x direction, this is the y direction, and this is the z direction. We keep our life simple and say at y equal to 0, this is y equals h, okay. There is no pressure gradient, okay, which is driving the flow, only the upper plate moving is driving the flow. So, what we have is there is no dp by dx, dp by dx is 0, okay. And you can do the same simplifications which we have done before. Assume system extends to infinity in x and z directions. So, again I am trying to keep my flow field one dimensional, things are moving only in one direction, okay. So, I mean these assumptions basically help me do that. So, there is nothing in the z direction and in the x direction sufficiently long, so that I can get fully developed velocity field, okay. The reason why I want x to extend to infinity is because I want the velocity field also to be fully developed, no changes in x direction. So, I want you to look at the equation of continuity, and from there, from equation of continuity you will infer Vy is 0. We have done this before, the velocity in the y direction is 0, okay. I mean you say fully developed, so one term goes to 0, does not change in z, therefore it goes to 0, and only thing remaining is the y component of velocity, and because of the no penetration condition you will have velocity is 0 at the boundary, vertical component of velocity is 0 at the two walls, and therefore it is 0 everywhere, okay. This argument we have made before. So, the next thing we are going to do is look at the x momentum equation, okay. Why x momentum? Because that is where the flow is, that is where all the excitement is, okay. So, because it is Cartesian coordinates, I will write it down, dou Vx by dou t plus Vx dVx by dz x plus Vy dVx by dy plus Vz dVx by dz equals minus dP by dx plus mu times d squared by dx squared plus d squared by dy squared plus d squared by dz squared of Vx, okay. This is the equation of momentum in the x direction. Again we have steady state, okay. If we assume steady state, this goes to 0, Vx is not 0, but because it is infinitely long, dVx by dx is 0, there is no change in x direction. So, this is 0 and therefore this goes to 0, this is 0 because Vy is 0, okay. This is 0 because Vz is 0, there is no pressure gradient driving the flow, so that goes to 0, and again this will be 0, this will be 0, and what you are left with is d square Vx by dy squared equals 0, okay, multiplied by mu, but viscosity is not 0, therefore this has to be 0. Now, you can definitely integrate this equation, Vx does not depend on y and z, so Vx Vx is independent of x and z, fully developed flow, therefore, it does not change with x, does not change with z. So, I do not have to worry about partial derivative, it is a total derivative, it depends only on y, okay. So, I can integrate this, I will get Vx is equal to Ay plus b, where A and B are constants. Because this depends only on y, A and B are constants. Supposing this partial derivative, then when you integrate, what happens? Those constants can be functions of x and z, okay. So, remember that. So, because I mean, so every step, I mean, there is a reason and a rationale for doing it. It is not that I am just converting it. When I convert it, there are implications. When it is total derivative, the constants, these are constants. Since we have a total derivative, okay, not partial derivative. If it is partial derivative, those constants can be functions of the other variables, okay. If we had a partial derivative, then A and B would be functions of x and z, okay. So, they are not functions of x and z, they are constants, and now you know how to do it. You just have to put the boundary conditions. What are the boundary conditions? Vx equals 0 at y equals 0 and Vx equals V naught at y is equal to h, the upper wall, okay, because I am moving it at a constant velocity. I am applying, I have a stationary wall, I put a layer of liquid, I keep another wall on top and I am moving it at a fixed velocity, okay. In order to apply to a fixed velocity, I have to apply some force, and depending upon the viscosity, this force is going to change. So, now you can definitely solve this very complicated problem and find Vx is equal to what? V naught times y by h, okay. The velocity is linearly varying from 0 to h to V naught. At y equal to 0, I get velocity is 0, satisfies the Nocil boundary condition, and at y is equal to h, it satisfies V naught. That is my velocity profile. Now, this is my velocity profile varying linearly. What I am interested in is what is the kind of force that I have to apply, okay. In order to find out what is the force that I have to apply, I need to calculate what is the tangential stress which is being exerted by the fluid on the plate, okay. And so, I am going to apply, so how do I find that? How do I find the tangential stress? This is my y direction and this is my x direction. So, this is at y is equal to h. I am interested in the tangential direction. So, what component of shear stress am I interested in? I am interested, the outward normal to the surface is in the y direction. The direction of the stress is the x direction. So, the stress component of interest to me is tau yx, okay. Tau yx is the shear stress component acting on the top wall in the x direction. Is this clear? So, I mean, you need to know what exactly you are interested in. you don't do tau yy, because tau yy will give you the normal stress component. I am applying the force in the horizontal direction, so I want tau yx, okay. So the first subscript tells me the direction of the outward normal, second subscript tells me the direction of the force or the stress. So now if you know what the area is over which, of course in this particular problem area does not make sense because it is infinitely long, okay. So supposing you have, just imagine that you are applying the shear stress is acting on a specific area, then what will be the force which you are exerting on the plate? It is just tau yx multiplied by the area, okay. So tau, the force on the top plate is equal to tau yx multiplied by area, and if the fluid is Newtonian, tau yx is given by mu du by dvx by dy plus dvy by dx times area. So in our problem we already know Vy does not change with x, Vy is 0 everywhere. So always remember you need to have both these terms, because when I did that del V plus del V transpose, I got, how do I get this? Because del V by del V transpose, this is del V, this is del V transpose, okay. This is 0 because my flow is one dimensional. That is the reason people have all these viscometers operating at very low shear rates, so that the flow is one dimensional, okay. Then you have, this is something which I can measure experimentally, force mu, and dvx by dy is, I already know what is dvx by dy, which is v naught by h multiplied by area. Sorry, this is, I'll call this area. Why do I call this area? Because I already have an A there, I don't want to get confused with that A and this A, okay. So now if you can measure the force which you are applying on the top plate, and you know what is the velocity, you know what is the gap between the plates, you know the area over which you are applying, you can calculate what the viscosity is, okay. This is the general idea, okay. I have illustrated this idea for a rectangular geometry, okay. Of course the question is, how can you have infinite plates, and I mean you can't keep going forever, right? How can you measure experimentally? So what people do is, they will translate the same idea into cylindrical coordinates, where the surface moving will be the surface of a cylinder, okay. And then that is what we are going to do in the next class. We will see how this concept can be experimentally realized by looking at a cylindrical geometry. Same concept, everything is same Couette flow. You will have one dimensional flow, one wall is moving, one wall is stationary, you will find what the flow field is, and you will do the calculation of the shear stress. Then the tau r theta, or whatever tau we are looking at, which we derived earlier today, will be used. The tau will be used, and then we will calculate the torque in this case, okay. We will do that tomorrow.